So, in the previous lecture, we have derived how to derive the steady state waveforms of a DC-DC buck converter. Now, we'll just quickly see the ratings of the parameter or the selection of parameter ratings for designing a DC-DC buck converter. So, ratings of the power for deciding the ratings, we'll have to see two things. First is the steady state operation, second is the transient operation. In steady state operation, as we saw in the last lecture, as per the waveforms, we can select the rating of a device, for example a switch. So every device has two types of rating: voltage rating, current rating. So if the voltage across a switch when it is off is V in, it means that the rating of the switch should be at least greater than V in. Then only that device can operate in safe condition. And also we have to see the current, maximum current which flows through the device. So as you know that a load is sitting at the output of a buck converter, so the current will be mostly governed by the load current. So that's why we have to see how to design or how to select the different power components based on the steady state and transient conditions. So here I'll write device, voltage, current, percentage voltage and percentage current rating. For the switch S1, we saw that when it is off, the diode is forward bias and the voltage across it is V in. So it should be rated at V in. And as we know that this is inductor current, so inductor current equals to the input current or the switch current when the switch is turned on, and the maximum value, we'll see the maximum value. The maximum value of inductor current is IL max. So it should be rated at IL max. Percentage of, let's say 25% of nominal margin in voltage is permissible. For current it should be 10 to 15%. 10 to 15%. For the duty ratio, for the diode D, let's say we denote the diode by D1, not D, because D is a duty ratio, steady state duty ratio, so we'll have a confusion. So for the diode, if the switch is on, diode is reverse bias, so the voltage across it is V in. And similarly the current, it should be rated for the same current rating of IL max, same 25% and 10 to 15% it should be rated for. For the inductor, the voltage should be V in, again same thing. For the capacitor, it should be rated for V naught instead of V in, and it should be rated for which current? Capacitor current is having average value of 0, so it should be rated for the RMS current, that is I naught RMS current. So 15% of voltage and 20 to 25% of current band. That is for typical electrolytic capacitor, permissible limits for polarized or electrolytic capacitor. Now, not only steady state but also transient requirement should be considered for deciding the rating of these circuit components. So the transient means, let's say there is some change in the circuit, some load is changed, or suddenly some input voltage is changed. So transient occurs at that time. It occurs for a very short time. Steady state means once the transient is happened, once the controller states are tracking its new steady state value and the states of the converter are known, that is called as a steady state. Or let's say the variation of a particular state is within permissible limits, let's say it is between 2% of limit, that is a steady state. So these are the steady state rating, these are the rating of the converter as per the steady state. For transient, we have to see different type of transients. First is a static transient, second is on-off transient, and the third one is normal, like change of load, change in input voltage transient. Now we see what should be the range of operation. So for that we have to derive a relation of so now to derive the preferred range of operation, what should be the range of operation for the converter? T versus M of T. This is 1. MD is also 1. MD means V naught by V in. So what happens when if we operate at different loading conditions, or you can say different duty ratios? It is observed that if the duty ratio is selected preferably high, near to 1, so typically duty ratio cannot be 1. 1 means that the switch is on for the whole switching time. This is not valid because then the inductor will keep on continuously charging. There is no discharging state of it. So typically you can consider it up to 0.9 or 0.99. So if the converter is operating at a very high duty ratio, say 0.99, it means that the on time is very high and the off time is very less. So in order to maintain the volt second balance, the voltage across the inductor during the on state will be less. Why? Because the area of VL on into T on should be equals to VL off into T off. As TL on is very high or greater than TL off, so VL off should be very high than VL off. So in this way the converter will operate. But generally it is observed that if a buck converter is operated for a higher duty cycle, then the peak current of the inductor will reduce, and thus it will result in the reduction of the weight and volume of the inductor. Because inductor is wound on a core. The core can be toroidal core, E core, and different types of cores. Again, it depends on the core material, like what should be the flux density, either sandust core, ferrite core. Then if our requirement of inductance value is very high, then how to add the air gap. So that is design of inductor. But it is observed that the courses can be reduced to limit the peak flux, which will result in the reduction of the cost, weight and volume. So it was observed that generally this is the preferred operating range of the converter for a practical converter. Now what happens to the ripple current rating of the capacitor? As the capacitor's value is increased, the rated ripple current or delta V naught across the capacitor is less. So they can be cheaper and smaller in size compared to the other equivalent ferrite type metal filled capacitor. And metallized or ceramic capacitors have a higher ripple current rating but are costly and bulky in size. As D increases, the ripple across the capacitor, C naught ripple, will be reduced. So that's why this is the preferred range of operation for a buck converter. Means you can operate at below less than 50% duty ratio, but it has its own advantages. So this was the operation of DC-DC buck converter. So instead of calling this section as design of second order DC-DC converters or design of buck boost and buck boost converters, I will call this section as designing of continuous operation of DC-DC converter, of basic second order DC-DC converters. So we are done with the first type of converter. Now we'll see boost converter. Boost converter. Boost, as the name says, boost. It means that the assumption is, very first assumption is V naught is greater than V in. This should be the first assumption. A buck converter should do only bucking. A boost converter should do only boosting. And then as per that, we have to set the volt second balance and current second balance, and we have to see where to place the inductor or the energy storage elements. Based on the placement of the inductor, we find different topologies of the DC-DC converter, where you can see the bucking or boosting actions. So in a boost converter, what happens is that this is the input voltage, input current, the inductor is placed at the input side. So this will be L, this is VL, this is IL. The switch is replaced by the inductor. This is S1, this is IS1, this is VS1. After this we have a diode, capacitor, and then a load. This is C, this is R, variable load. That's why my load is changing. This is IC, this is V0, this is diode D1, so this is ID1, this is VD1 plus minus. This is the circuit of a boost converter. So let's first draw all the waveforms of a boost converter. We'll start with the switching pulses. I'll draw only two pulses. This is switching pulse to S1, switching pulse to S1. This is 1, 0. This is 1, this is 0. Again 1, 0. Then we have to bring it down. So after gate pulses, we'll start with the first energy storage element, which is the inductor. We'll see the voltage across the inductor. So when the switch is on, the voltage across inductor is V in. So this will be V in. We'll use one color. This is V in. This waveform belongs to VL, and when the switch is off, again the inductor current will force the diode to be forward biased. The voltage across inductor is V minus V0. As V0 is greater than V in minus V0 is negative. So it will be like this. this value is V in minus V naught. Again, this is A1 and this is A2. So now let's start with the next state, or here only we will draw the waveform of the inductor current. As the voltage across inductor is positive, the current will start rising. Then it starts falling, then again it starts rising, it starts falling, and so on. So this is called delta IL. This is IL min. This point is IL max, and the average value this average value, this is capital IL, and this waveform belongs to IL. This is the average value of the inductor current. Average value of the inductor current. So later we'll derive the equation of volt second balance, the relation between V0 and Vin. But first let's draw and complete all the waveforms. So this is done. Now let's go to the switch. So when the switch is on, the voltage across it is 0. When the switch is off, the diode is forward bias. So what will be the voltage across the switch? It will be plus V0. It will be plus V0 because the diode is forward biased. It will be 0 and V0. So it is 0 and V0. This is Vs1, where this value is 0 and this value is what? V0. Then let's draw the current through the switch. So when the switch is on, diode is off, the inductor current is equal to the switch current. When the switch is off, switch current is 0. So it means that the plus thing, this is the current through the switch. Now this waveform also has its own average value, which is denoted by this. I will write here. This average value is capital I S1. So again, this is IL max and this point is IL min. As you know that the average value of inductor current is a capital IL, so the average value of this current will be, if you consider the steady state duty ratio, it will be 1 minus D into, sorry, not 1 minus D, it will be D times capital D into IL. That is the average value of the current through the switch. Very easy. If the average value of inductor current is IL, then average value of the source current or the switch current is capital D into IL. Why? Because during on time only the switch current equals to the inductor current, rest it is half. So that is the case. Now switch is over. Then let's see the diode. So when the switch is off, diode is when the switch is on, diode is reversed bias. Then the voltage across the diode will be what? It will be, so V, if the switch is on, the diode is connected in the reversed fashion across the output. So it will be minus V0. So voltage across diode will be minus V0, and when it is on, forward bias, it will be 0. Because when the switch is on, it is minus V0. So it will be like this. Where this is 0 and this is minus V0. This is the waveform of VD1. Now let's draw the current through the diode. The current through the diode, when the diode switch is off, diode is off. When the switch is off, diode is on, and that current, diode current, equals to the inductor current. So this is its average value. This average value is capital ID1 is capital 1 minus D into capital IL, where this is again IL minimum, this is IL maximum. So this is the this thing, waveform of the diode. Now comes to the last element, that is the capacitor. We start with the capacitor current. We know that ID, diode current, equals to ID1, will write ID1 equals to IC plus I load. IC plus I load. So again the same, this is I load constant, ID is this, so its average value goes to the load. So the waveform of ID will be shifted in such a way that its average value is 0. Again, the current second balance says that average value of the inductor, the capacitor current should be 0. So it had to be shifted in such a way that the quantity by which we are shifting the diode current is equals to the load current itself. Then only it will have 0 average value. Then if we draw the waveform, it will be like this. So this waveform, we are bringing it down like this. So okay, I'll use the same purple color. It will be like this. It is shifted down. So now this point becomes what? IL max minus what? It is shifted by the quantity which is equal to the load current only, minus I load. This becomes IL minimum minus I load, and this term becomes I load, which equals to V0 by R. So now this becomes the area 3, this becomes the area 4. correct? Now we'll plot the last quantity, which is nothing but the capacitor or the output voltage. So this waveform was for IC. This waveform was for IC. So Vc of t equals to 1 by C integral IC of t dt plus Vc naught. So we have to integrate it. If you integrate a falling slope, it will be a falling polynomial like this. And if you polynomial of second order, and if you integrate a constant term, what will be? It will be rising edge. It will be a straight line. So it will be like this, and then this will be like this, and again straight line, and then a curved, again straight line. So this will be V naught. This is delta V naught. This is V naught max, and this point is V naught minimum. So these are the waveforms of the boost converter. Using volt second balance, what do we get? VL on into T on plus VL off into T off equals to 0. What is VL on? VL on is V in. So V in into D into T switching plus what is VL off? It is V in minus V naught. So but V naught is greater than V in. So let's write minus of V naught minus V in. So this plus sign will go. It will be V in into D switching minus V naught minus V in into 1 minus D into T switching will be 0. T switching will get cancelled. Sending this to the right side, we'll get V in into D equals to 1 minus D into V naught minus V in, because V naught is greater than V in. If we send V in here, it will be V in, D will be common, so plus 1 minus D equals to 1 minus D into V naught. This will get cancelled. So therefore V naught will be V in by 1 minus D. And as D lies between 0 to 1, so V naught lies between infinity to what? V in. This is the range of the output voltage for the boost converter. So here M of T will be V naught by V in, which is the steady state DC transfer function. It will be 1 by 1 minus T. If you plot it, then you will get like this. Like this. This is D. This is M of T. It will start, M of T is 1. It will start with 1. Why? Because V naught equals to V in for least D, when D is 0. Then it is a rising this thing. When this is 1, the gain will be very high. Like this, the gain DC can be very high. For 0.5 it is actually 2. Like this. Okay. Like this. So let's do the current second balance or amp second balance. Using amp second balance, what is the amp second balance? IC on into T on plus IC off into T off equals to 0, which means that A3 equals to A4, mod of A3 equals to mod of A4. Here we don't take any sign. So A3, what is the area of A3? Is the rectangle. So the area of rectangle is what? L is length into breadth. The length is the time. So this thing is 1 minus d into t switching, and this thing, sorry, this is d into t switching, and this is 1 minus d into t switching, and this is the whole time period, one switching time period. So A3 will be what? Length into breadth. The length is the time, that is d into t switching, into what is the y coordinate? It will be the load voltage only, because the waveform of diode current is shifted by the load current. So it will be V into V naught by R, or let's say it is I load, equals to A4. How we can write A4 is? A4 is like this: rectangle plus a triangle. So it will be half into 1 minus d into t switching, half into base into height. First we'll find the area of the height. What is this height? IL max minus IL minimum, this thing. This is delta IL. Okay, so this is delta IL plus area of the rectangle, length into breadth. So 1 minus plus 1 minus d into t switching into what is this remaining area? This whole is 1 minus so it is IL minimum minus I load minus I load. So if we cut t switching, then we'll get d into I load equals to 1 minus d by 2 into delta IL plus 1 minus d into IL minimum minus I load. If we take 1 minus d common, it will be delta IL by 2 plus IL minimum minus I load. So we know that this is capital IL and this is delta IL. So we can write IL minimum as capital IL minus delta IL by 2, and we can write IL max as average value of IL plus delta IL by 2. So if you substitute, it will be d into I load is 1 minus capital D into delta IL by 2 plus IL minimum. IL minimum is capital IL minus delta IL. It's not IC. IL by 2 minus I load. This will get cancelled and we'll get equals to 1 minus capital D into capital IL minus I load equals to D into I load. If we solve, if we send I load term here, it will be, and if we take I load common, it will be capital D plus 1 minus D equals to what? 1 minus D into IL. So I load equals to 1 minus d. So we can write directly, we know what is I load, now we want to find what is capital IL. So capital IL is I load by 1 minus t. Now in this case, I load was the output current, IL equals to the input current, IN equals to IL. So the average value of input current equals to average value of output current, which is I load, divided by 1 minus t. And V naught is V in by 1 minus t. Correct? So it means that this is output voltage, this is input current, and this is input current, this is output current. So this is the DC gain for the average value of currents between input and output using amp second balance, and using volt second balance you will get the relation between input and output voltage. So if we see the rating, it will be device V I delta V delta I. We'll say steady state ratings. So S1, D1, L and C. For S1 it is V naught. This is IL max. I max you can write below or above, that is not a problem. 25%, again 10 to 15%. So for D1 it is same. For D1 the current is IL max. In the buck converter it was different current. Again it is 25%, 10 to 15%. Now for inductor we have two special cases. It is V in or V naught minus V in. This is for D less than 0.5. This is for D greater than 0.5. So the current is again IL max for both the cases. For both the cases 15%, 20 to 25%. For capacitor V naught, now the current is V naught I naught RMS still 15% and 20 to 25%. These are the steady state ratings. Now what is the preferable range of operation of the boost converter as per the DC voltage gain? This is 1, this is 0.50, so this is 1. For 0.5 the gain is 2, this is 2. So the preferable range of operation lies here. There are two bands. This is one. So let's say this is around 0.7. So 0.7 to 1 and almost 0.4 to 0.35, 0.3 to, oh sorry, that is some mistake. It is 0 to 0.5 and 0.7 to 1. This is the preferred range of operation. This zone 1 is preferred operating range. Now let's see what happens in the zone 2. For the buck converter, we saw that it is advantageous to run the buck converter at higher duty ratios because the size of the components and the stresses, voltage and current stresses across the devices will be reduced. The ripples will be reduced. But in the boost converter, what happens is that for higher band, let's say this is the band from 0.7 to 1. For this higher band, so what happens is this will result is this is called as non-practical zone, not applicable. Why? Is because it needs a bulky inductor. We'll see in the next lecture how to decide the inductances. So high current and voltage rating. We'll need a higher voltage and current rating for the same output power, and it will also result in ESR of the inductor. That's why the reason is we should not operate boost converter at higher duty ratio. Why? Because why I'm saying that for operating the boost converter at the higher duty ratio will result in higher voltage and current ratings for the same power rating is because the device voltage, the voltage and current ratings of a device are proportional to the converter's overall rating. That's why, that is the reason. And for a boost converter, say it is of 1 kilowatt application of power, and let's say the voltage V1 by V2 input output voltage gain is say 10 is to 100, then the current will be 100 is to 10 because we saw the relation. It is an inverse relation between the current. So it will be 100 is to 10. Then the device rating, then if the rating of the input output current is 100 is to 10, it means that the input current is very high because the voltage is very low. Then the device, in this case, where is the device kept? Device is kept near to the inductor. Device means the switch. The switch is kept near the inductor, which means that the device or the switch will need 150 volt to 120 ampere. That's why there is a requirement of very high ratings of a switch. And the finite resistance of the inductor, which if considered, will result in the non-linearity because V0, the ratio of V0 by Vin, that is 1 by 1 minus D, there will be some additional non-linearity which is due to the equivalent series resistance of the inductance. That's why this problem occurs when the duty ratio is very high. So that's why we should not operate a boost converter at a higher duty ratio. Now let's see what happens at the lower duty ratio. At lower duty ratio, the ripple components in the inductor, output capacitor, and thus at the output voltage will be minimum if D is very less because it's a function of D. We have to derive it. We'll see the derivation in the next classes, and then we'll conclude on the operating range of the DC-DC converters. So if the duty ratio is very less, it will result in the advantages including peak current rating of the inductor. The core size will be reduced to limit the peak flux, given that the material, the magnetic material or the core material is constant, and it will result in reduced cost, weight, and volume. Then the ripple current of the capacitor will be reduced. It will be cheaper and smaller for the same farad value, and as D tends to 0 or D is very less, the output capacitor ripple will be reduced. That's why you should operate a boost converter at comparatively less duty ratios. Similarly, there is a third type of converter that is called as buck boost converter. The circuit diagram is like this. S1, IS1, IN, VS1. Then this goes to the inductor which is sitting in the parallel lane. VL plus minus L, IL, and then we have a diode like this. This is the diode D1, this is VD1 plus minus, this is I D1. Then we have a capacitor like this, and then a load. This is I load, this is C, this is V0, and then this is IC. So this is a boost converter. We'll see the voltage waveforms of a boost converter for this particular arrangement. First start with the switch. Let's start with the switching pulses. One, 0. So let's start with the first state, that is the inductor. First energy storage element, that is the inductor. When the switch is on, what happens when the switch is on? The switch is on, again diode should be reverse bias. So the switch is on, plus terminal gets connected to the cathode of the diode, which will make it reverse bias, so it is reverse bias. So then the voltage across the inductor will be V in. It will be V in. This is V in. When the switch is off, the inductor will force the diode to turn on. In that case, the voltage across the inductor is plus V0. And here, as it is a buck boost, so V0 can be less than V in and V0 can be greater than V in also. But in any of these cases, the waveform of the inductor voltage should go beyond the negative axis, which means that it should be negative. In this case, the voltage across inductor during the off state is V0 only, plus V0, which means it will be above the zero axis, but we want it below the zero axis, like this. This should be minus V0. Then only the volt second balance will occur. So what happens is, this polarity has to be reversed. It has to be reversed like this. ID1. Now this will be IC. This will be IL coming from down. This will be I load, and this will be V0. So we have to reverse the polarity for the volt second balance to occur. Now this is A1, this is A2. Okay, let's draw the current through the inductor. Again it will be rising, falling. This is IL max. This will be IL min. and this will be capital IL. This waveform belongs to S1, this waveform belongs to inductor current and voltage. So moving on to the next state, let's see the switch. When the switch is turned on, the voltage across it is 0, so this will be 0. When it is off, the diode is forward bias, so the voltage across the switch will be what? It will be V in minus V naught. It will be V in minus V naught. So it can be either this or this. Why? Because V naught can be greater than or less than V in. So this will be V. I'll write with the blue. So this will be V in minus V naught or minus of V in minus V naught. This is for V in greater than V naught, and this is for V naught greater than V in. Why? Because it can do both boosting and bucking. This is waveform of Vs1. Again, the current through the switch will be what? The switch is on, diode is off, Is1 equals to IL. So it will be again like this. So the average value of this will be capital Is1, which will be D times IL. Again, this is IL max, this is IL min. So switch is done. Now let's go on to the next element. Diode. So when the switch is on, the voltage across the diode with the reverse polarity. Now the diode is reverse bias. The voltage across the inductor is equals to the input voltage. So the voltage across the diode, if we apply KVL, it will be like this. It will be like this. Plus minus V in, then minus plus VD1, again plus minus V naught. And these three circuit elements are connected in series. We have to find VD. So if we go doing the loop analysis, it will be, let's say we are going from minus to percent, so we'll say it minus. So minus of V in, minus of VD1, minus of V naught equals to 0. So what will be VD1? It will be minus of V naught plus V in, which is negative. Even if V naught is greater than V in or V in is greater than V naught, its polarity is negative. So this is when the switch is on. So it will be like this, and it will be 0 in the either case, because in that case the diode will be turned on. This will be minus of V naught plus V in. So this is waveform of VD1. Now how will be ID1? It will be similar to the inductor current again. If the switch is on, diode current is 0, and if the switch is turned off, diode current is on. So in that case, inductor current equals to the diode current. So it will be like this. So this is capital ID1. Again this is IL max, this point is IL min. So capital ID1 will be 1 minus capital D into capital IL. Now we'll go to the last element, that is the capacitor. We'll see where the load is placed. If you apply KVL, so what we'll get is the nodal analysis will be like this. So at this node, this is ID1 current, this is IC current, and this is I load current. This is ID1. So I load plus IC equals to ID1. So we have to find IC. IC is ID1 minus I load. Again, so IC1 we have to shift it down. This will be IC. This will be IL max, IL min, and again it is shifted by its value, which is I load, which means that the average value of the, so ID1 has average plus ripple, but not the complete ripple. ID1 is 1 minus capital D times IL1. You can call the current through the inductor as ripple plus some average value, and the current through the diode can be the half ripple during the off time plus average value. That average value goes to the load, and the remaining off ripple goes to the capacitor, just like a boost converter. So again it is A3, A4, like this. Again the same analysis. So as the current, so one last waveform is remaining, that is the V0 voltage. Again we have to integrate it. So this will be straight line, straight line. This will be a falling curve, falling curve. This is V0, V0 minimum, V0 maximum. This is average value of V0, capital V0, or like this, and this is the delta V. This is delta V0. Similarly here we have delta IL. This is delta IL. So as the current waveform is same, so using amp second balance, what we'll get is the same thing which we got in the boost converter, that is IL is I load. IL is I load by 1 minus D, but there will be a negative sign multiplied to it because the polarity is reversed. Or what you can do is you can avoid this negative sign and change the direction of the current in this fashion. So now using the minus sign will appear in the volt second balance. So VL on into T on plus VL off into T off equals to 0. What is VL on? It is V in, and during off it is minus V0. So V in into T switching minus V naught into 1 minus t into t switching will be 0. So t switching will go on. So V in into t equals to 1 minus t into V naught. Therefore V naught is d by 1 minus t into V in. This is when with the polarity reversal. If you don't reverse the polarity, then negative sign comes. This is without the polarity reversal. So these were the steady state waveforms of the buck boost converter. Now m of t will be what? D by 1 minus t. This switch, so it will be like, if d is between 0 to 0.5, it will act as a buck converter. If d is between 0.5 to 1, it will act as a boost converter. This we can verify easily by putting any value of d, which is once which is less than 0.5, another one which is greater than 0.5, and then you can easily get. If you plot md with polarity reversal without polarity reversal wala thing, what you will get is that this is capital D, this is m of t, and this waveform is like this: -1, -2. For -2 it is 0.25, and so on. So this is the DC transfer function for a buck boost converter. So the disadvantage of a buck boost converter is its reversed polarity. So see, either if you don't reverse the polarity, the volt second balance will be invalid. So somewhere a negative sign will come. Let's assume that the polarity is not reversed, the waveform which we have drawn are correct. Then we have to intentionally add a negative sign in the volt second balance waveform. In the expression, not in the amp second balance. So this is the thing. And the operation of a buck boost converter you can easily see. So as I said, at V0 can be more than or less than V in, the waveform of V1 will be changing, as I have drawn two possibilities here. So if we, as buck boost converter is a buck plus boost derived converter, so the range of operation will be a combination of both of these things. That is, it will have two ranges of operations in these two strips. So this is for buck mode. It is valid for buck mode and invalid for boost mode, this particular strip, and this strip was valid for both buck and boost mode. So this is not preferable, and this one is preferable zone of operation. So the same disadvantage and advantages of the buck and boost converter will apply to this buck boost converter. So the preferred range is like this. So it will be slightly enhanced range. It is from say 0.3 to this is 0.7 actually. 0.7 is the preferred range of operation of this buck boost converter. So for 0.3 it is almost minus 0.5. So this is the analysis of the continuous analysis of the three basic buck boost and buck boost converters. In the next lecture, we'll see the discontinuity, the discontinuous operation. So, and also the design of the different parameters, like what should be the inductance value, what should be the capacitance value based on the given requirement. We know we already discussed. So in this lecture, we discussed the steady state analysis of the boost and buck boost converter, along with the preferable range of operation of the buck converter and the similarity between them, the preferred range of operation for all the three converters, the steady state waveforms for all the three converters, the analysis, steady state analysis we have done of all the three basic second order DC-DC converters in the continuous time domain. Now we'll see the discontinuity which happens in the buck boost converter, its disadvantage and its advantages, then designing of the inductance, critical inductance, capacitance, etc. that we'll do in the next class. Thank you.